Okay, everybody, thank you for bracing the weather today and coming down on this cold day to the Institute. Today, it is my absolute pleasure to welcome Dr. Dan D'Orazio to the Institute. After completing his PhD in Columbia in 2016, Dan was awarded an Einstein Fellowship, which he took to Harvard, before moving on to an assistant professorship at the NBIA in Denmark. Dan has since returned stateside and is currently based at the Space Telescope Science Institute, where he is an expert on supermassive black hole binaries, circumbinary accretion processes, and stellar mass compact object binaries. And in particular today, we will be hearing about the search for supermassive black hole binaries driven by gas and gravitational waves, and also the possible multi-messenger signatures that we should all be looking for. So please do join me in welcoming Dan to the stage.
Well, thank you very much, Colin, and thanks all for coming here today. And well, thanks a ton for inviting me. I really look forward to telling you about, well, supermassive black hole binaries. And specifically, this talk, I want to focus on what we can learn for the multi-messenger search for these elusive systems from simulating, modeling, understanding the interaction of these binaries with gas. All right, so kind of the subtitle to the subtitle of this talk today is Lessons from Binary Accretion. And I hope that will become clear what these are soon. So you can already see the images I have up here are a number of images of this binary gas interaction. Some of them are real in a telescope, and some of them are real on a computer. And as we go, I hope it becomes clear which is which. I'll leave that to the viewer. All right, so to start, supermassive black hole binaries, why are we thinking about this? I like to start actually with this analog to the electromagnetic sky that you might see in an Astronomy 101 class, where you look in frequency from radio to visible to gamma rays. What are the sources of electromagnetic radiation and how do we detect them? This is the gravitational wave analog, the gravitational wave sky, which you can see goes from very low frequency gravitational waves that might be sourced at the beginning of the universe to the very high frequency gravitational waves that were detected in the last decade by LIGO, Virgo-Cagra collaboration. Right, so these gravitational waves at hundreds of hertz. These are from the mergers of black holes and neutron stars, stellar mass black holes and neutron stars. And the detections of hundreds of these now has really revolutionized the field. It's created a new field, gravitational wave astrophysics. And on the astrophysical side, we're busy now trying to figure out how are these formed? How are these black hole mergers formed? And how can we use those as tracers of astrophysics? So this will continue to be extremely exciting in the future decades. But what I'm focusing on today is what I think is another extremely exciting future of gravitational wave physics, and that is the low-frequency gravitational wave sky. And so how do we detect low-frequency gravitational waves? There are two main methods, or detectors. One at these kind of nanohertz frequencies is the pulsar timing arrays, which are galactic scale detectors where we're timing millisecond pulsars, and these are our clocks, which we can use to detect these parsec wavelength, the gravitational waves coming through our galaxy to Earth. So these are the radio pulsar timing arrays. And then at millihertz frequencies is the laser interferometer space antenna, which will launch in the 2030s. So this is the exciting future, but it's also now. The pulsar timing arrays have presented strong evidence for a background, this nanohertz background of gravitational waves, and that was only in 2023. And LISA is no longer an idea. It has been adopted by the European Space Agency to launch in the 2030s. Okay, so these are our detectors that are coming online, or already online in the low-frequency gravitational wave sky. And of course, the sources, one of the main sources, hopefully there are exciting things we're not thinking about, but the main sources are the supermassive black hole binaries. And I'll get to which one of these different types of detectors can detect. But first of all, the kind of picture of how are these formed astrophysically. Right, so this is the standard three-step picture. Supermassive black hole binaries. They exist in galaxies, and when galaxies merge, they can sink to the center of this new galaxy and form a bound binary there. Right? And if that bound binary can get close enough in separation, then step 3, gravitational waves can very efficiently carry away energy and angular momentum and merge the binary in an event that we'll see with LISA or perhaps the pulsar timing arrays. Okay, but of course we got very excited there in the all-important step 2, and that is how does the binary get close enough once it's formed to emit efficient gravitational wave radiation and merge before a Hubble time, essentially, right? So this step 2 has been called many things. One is the final parsec problem. So I wouldn't say that the final parsec problem, as it was originally stated, is still a problem, but there's still a question of all the ways that you can get these two close enough, which are the ones that happen in nature, right? And so to understand that, you need to understand the interaction of these binaries with their environments. One of the main ones, the one I'm focusing on today, is the environment of a gaseous disk accreting onto that binary, right? There are also stars, and we can save that for discussions afterwards. Today will be, how do we understand this gas interaction? So this is a movie we'll see many of throughout, of a binary, swirling up this gas disk that is accreting onto it. And what can we use modeling of this interaction for? Well, one, just like a satellite decays its orbit in the Earth's atmosphere, the binary's orbital evolution will change due to this gas interaction. And you need that to help make population predictions for merger rates or any number of ways that you might want to detect these systems. And speaking of detecting them, we know that gas accretion creates one of the brightest, was the most efficient way to convert matter into energy in the universe. We see the quasars at the edge of the universe. So we can also use these types of calculations to understand how we might look for these in electromagnetic radiation, as well as gravitational wave radiation and combinations of the two. All right, and of course, if you can identify members of a population and predict how they get there, you want to use these together to do demography and understand this whole process of supermassive black hole binaries coming together, how they mutually evolve with their galaxies over cosmic time. So this is kind of the layout, the motivating picture of why what the rest of this talk will look at, this interaction of gas and the binary, what the bigger picture is. But before I jump into some of this modeling and what we're learning, these lessons from binary accretion, I actually want to spend a little more time on this in a more quantitative sense to get a sense of scale. Specifically, when is gas accretion important onto a binary? Maybe more specifically, we have angular momentum is a common in the universe. When are disks, gas accretion disks on the binary important for the kind of life of this binary from galaxy scales down to merger? Okay, so the way I'm going to do that is with this seemingly complicated plot with a number of lines on here. This is what I call the space of binary orbits. So the y-axis is just the orbital period of the binary in the rest frame. And this is the total mass of the binary on the x-axis. And so this down here is where the binary merges. It can't exist here. And up here, it's a very large separation, which you can see from these orange dotted lines are kind of the physical separation of the binary in parsecs, one being up there. And the other important line here at the moment is this blue dashed line, which tells you how long that binary would spend in this part of the plot, how long it would exist if only gravitational waves were driving it to merger. So that is the Hubble time, and 1 year below that. Okay? So the first thing to make to distinguish is, when do we have a binary? So at large scales, you can imagine there is a kind of line below which the binary is bound compared to its environment. So we'll just say that for now. Above that is what you might call dual AGN, which this is an image of in the top left. An X-ray of the blue is X-ray for these accreting black holes, and the other colors are this kind of disturbed galaxy from a merger. So below that line is our binary. Okay, but now we want to focus on the gas disks. Where are they important? And the first thing to look at is on large separations. Any kind of thin disk, and now I'm just thinking of kind of radiatively efficient thin gaseous disks, will become self-gravitating at some radius. So there's a maximum radius where thin disks become self-gravitating, which means there's a maximum binary separation that you can surround in a non-self-gravitating disk. That's this shaded region. You can't have binaries this far apart and have a stable thin disk around them. All right, what about on the small scale? If we go to close separations now, there's a line below which the disk will likely not strongly interact with the binary. This is called disk decoupling. And this you can get an estimate for just by asking, at what point does the gravitational wave radiation drive the binary together more quickly than the gas can keep up? For example, due to viscous interactions. So when is the viscous time essentially longer than the decay time of the binary? And this will depend on things like what we'll talk about later in this talk, the thickness or aspect ratio of the disk and viscous properties in the disk. But you can draw it here at of order 100 gravitational radii. And now I'm simply just going to shade that region between what's a binary and where can the disk interact strongly with a binary as the realm of circumbinary disks, here in orange, in this space. And so what's the first thing to observe is that, as alluded to, this can help bring the binary to merger. It straddles the Hubble time. Okay. But then there's some other interesting things to notice here. First of all, as also mentioned, it seems that for these larger supermassive black holes, disks around these might be self-gravitating as opposed to standard non-self-gravitating disks for smaller supermassive black hole binaries. And I'm also going to draw on here a line that will come up in the end later in the talk, a line that kind of gives us an idea of what kind of disk do we expect, and this depends on energy and radiation in the problem. But essentially, for lower accretion rate systems, or I haven't really specified this, but if there's some accretion rate and this is lower, maybe 10 to the minus 2 of Eddington, then for smaller separations, the closer you can get down to the binary, you might expect these accretion flows to not be radiatively efficient and actually be hot, for example, advection-dominated accretion flows. All right, so add that one more line to this figure. And now what I want to do is put on top of this, where are things like the pulsar timing arrays or LISA sensitive in respect to where we have these different types of gas disks that can dominate dynamics or electromagnetic emission. All right. LISA at higher frequencies is sensitive to the mergers of these, welterweight supermassive black hole binaries here, whereas the pulsar timing arrays are looking at the in-spirals of the biggest supermassive black hole binaries in the universe, not even the mergers, the in-spirals. All right, so what you can see is that you have this interesting mix of the pulsar timing array progenitors, or even supermassive black hole binaries in the pulsar timing array band, might be this mix of either self-gravitating or these hot advection-dominated accretion flows. Whereas the precursors to LISA might also go through this hot instability, but they're likely sculpted pre-merger by these types of non-self-gravitating flows. And so just to give you an idea why that's important or what kind of observational effects you might get in LISA or the pulsar timing arrays, some highlights. Well, just like in LIGO right now, we're trying to figure out what astrophysical formation channels give you eccentricity and spin in this direction and that, so we can disentangle how they come together. That's the same game we're going to play here, and these gas disks may have an important factor in the rates and what kind of orbital parameters these binaries have when they come to merger. You also notice, although this is a schematic and you can change, to order a few where these lines are drawn, the gas can follow down into the LISA band. And what that can do is change your vacuum waveforms. So this is another kind of interesting study. It actually only very recently has been looked at more and more, and I'll talk some about this at the Bacall lunch. But you can get these perturbations to the vacuum waveform from gas, even for near equal mass ratio systems. Okay, for the pulsar timing array, we're not detecting individual mergers. We might detect individual sources. But right now, there is data and evidence for a gravitational wave background, which I'm showing here from one of the nanograv papers in 2023, where you have the strain from the background in each of these frequency bins, from low frequency to high. And on top are two different models. The purple line is a model where the binaries are driven only by gravitational wave radiation, and you get this characteristic f to the minus 2/3 power law in your spectrum of gravitational wave background. But if at lower frequencies, here, a disk or some environment is interacting with a binary, pushing it together faster than gravitational waves would, you lose some of that gravitational wave power, and you can have a turnover in these frequencies. And this, again, adds a diagnostic from gravitational waves alone on how the population is being put together. Okay. And finally, what I plan to talk about at the very end of the talk is that, of course, in this whole region, these accreting systems may be quasars. And so how do we tell if this accreting quasar is a binary versus a single? There are electromagnetic signatures we can look for here through this modeling in this regime of circumbinary disks. Okay. So what I plan to do for the rest of the talk, now that I've drawn all of these lines and shaded regions here and hopefully have some kind of picture, if you can interpret this, I'll ask people afterwards if they can interpret some of this. If we have this picture now for where the circumbinary disks are important and what they're doing for observational prospects, I want to jump into two parts in this talk. The first part is all about the dynamics. How do modeling these disk interactions bring us through this space? What have we learned from what we've done before? And it really is going to be a question of where are we going and what's a few lessons that we've learned from this modeling. And at the end, I'll talk about electromagnetic signatures. So first, binary disk dynamics. All right. So to model the binary disk interaction, we need a binary. So there's our binary with semi-major axis A, eccentricity E, total mass M, and mass ratio less than 1, M2 over M1. And so what is the end goal here? Well, in that potential of the binary, you want to solve the magnetohydrodynamical equations with radiation transport and so on. So what does that mean? You have some mass conservation, angular momentum, radial, vertical, momentum conservation, energy conservation. This is all coupled to what we think we need, magnetic fields and radiation, to accurately describe this system. Of course, many people in the audience are still doing this for a single black hole, right? And there's a long road here. So what I want to focus on is what I think is the simplest non-trivial approximation here, the simplest non-trivial problem to study for binary accretion, where we pretty much strip this down to the gravitational and hydrodynamics, the dynamics of the system, and ask if we can now strip this down to the 2D height-averaged equations, where we have mass conservation and accretion sinks and some viscosity prescription without magnetic fields, and we have the Newtonian binary potential. We can run this problem at high precision to convergence over a large area parameter space. And also, we'll relax this later, if we assume to start that we have a locally isothermal equation of state in the disk, then this simplifies the problem to really having only two disk parameters, a viscous one and a scale height h, which tells you how hot the disk is, how important pressure is. And then on the gravitational side, the binary side, we can scale out the mass and separation and the important parameters of the eccentricity and the mass ratio. So this is the system we've scaled it down to so we can explore all of this parameter space at high resolution and see where to go from there. Oh, good question. It just means that there's a very large outer boundary that we don't deal with. I could have started with a torus where the mass supply, angular momentum supply would disappear at some point, but I'm just have a huge outer boundary that keeps feeding in. All right. Okay, so what are some lessons of solving this problem over time? We've been doing it for a little while. And actually, if you go look at the binary parameters and start varying the mass ratio of the binary, you can start with a very small mass ratio. And instead of solving these equations numerically, you can look at linear theory to ask how does this small mass ratio perturb your background disk, right? And so short of it, here's a movie of this system in the co-rotating frame. Actually, it's just a picture, but it should look the same if it was a movie. And what you find is that perturber generates spiral density waves in the disk. Those spiral density waves apply torques to that small perturber. And generally, in most cases, the case we're thinking about here, the binary is pushed together at the type 1, so-called type 1 migration rate. This is famous in the protoplanetary literature, where that is Earth and Sun rather than small black hole and big black hole. Okay, but if we pump up the mass ratio, which is what we're working on doing here, then those spiral waves become nonlinear very quickly, and they shock right next to your perturber, and those shocks deposit angular momentum that can clear away gas and create some annular gap in your disk, which you're seeing here. This one really is a movie of, in the rotating frame, this 100 to 1 mass ratio system. Okay, and these, in most cases, again, also push the binary together through a process called type 2 migration. But now we want to go all the way up to equal mass ratio systems, still in the co-rotating frame of the binary. Now, in these cases, you find a highly nonlinear situation where the binary carves out this central low-density cavity. That's the black region. And furthermore, these cavities become eccentric. So what happens to the orbital evolution in this case? Well, first, I want to characterize this case a little more. And I'm going to go out of the co-rotating frame because I think it's more interesting or instructive to look at in this frame now, where the binary is twirling around. And what do you see? Like I already mentioned, the binary carves this really low density gap or cavity. And that you can really understand even from the restricted three-body problem if you integrate particle orbits in this potential of the binary, there's a whole region here where there are no stable orbits. That would give you a kind of circular cavity, even without pressure and a fluid approximation. But when we do have the fluid, what you find is that these streams, the binary pulls from the edge of this cavity, are flung off. Some of them go onto these little mini disks and accrete onto the black holes, but the rest of the stream impacts over here on the far side of the cavity, creating this eccentric structure that precesses on long time scales. Okay. Second point is that these you can run for long times, thousands, 10,000 of binary orbits, until they're in quasi-steady state, meaning the accretion rate that is set by the gas really far away matches the accretion rate onto the binary, even though this low-density cavity has been carved out, which you might think at first would keep gas from accreting. You still reach the same accretion rate you expect for a single black hole on to the binary pair. The same thing happens for the angular momentum current in the disk. You can also find a constant angular momentum current through the disk, and that couple is set by the couple of the binary to this cavity edge at the center. And this is all mediated by the gas streams in the way I just kind of laid out there. A stream is taken from the edge of the cavity, it falls onto the mini disk, some of it shocks, stays with the mini disk, the rest, most of it is flung back out. So still, what is the orbital evolution now for this kind of vanilla case? Equal mass, circular orbit, and an aspect ratio of 0.1. What we do, solve the equations of hydrodynamics that I've already laid out. For the system, we have gas density everywhere. Simplest brute force thing, we just sum up all the forces on the binary. Okay, so what do you expect? As I already showed you, linear theory and some of the simplest estimates tell you that you think the binary should be pushed together by gas. So detailed calculations, as maybe you know if you're in this field, have shown over the last 5 to 8 years now that some cases the orbit expands. And this was a big surprise. And there are ways that a number of people here in the audience even have worked out, there's Roman, of why this happens. And all I'm going to say for now is that this caused a bit of stir in the field where many people were working on this, trying to find some agreement on why this was happening and if it was right. And then in 2022, I held a KITP meeting pretty much on circumbinary accretion. And one thing that came out of that meeting was a big code comparison where everyone that was working on this problem set up this vanilla problem that we decided all on together and carried out this calculation with about 10 different codes. Mostly 2D, but there were also 3D calculations that were put in there as well, all viscous hydrodynamics. And at the end of the day, all I'm going to say for now is that they all pretty much agreed, which is an amazing output of a code comparison, a social and numerical experiment, I'll say. So that's a great question. It might look like, wow, these look all different. They're all at the same time, but because this instability of this eccentric cavity is pretty sensitive to some numerical seeding, it occurs different times in different codes. So if you could match them all up, they'd look closer. But that's what's happening with them looking a little different. Okay. Yes, so yeah, it was as direct as we could, given that there's SPH, grid, moving mesh. Yes. Okay, so what then does that mean for gravitational wave astrophysics if gas disks and all this time I put into telling you what they can do just push binaries apart? Well, there's what we found, because we can do this problem over a wide range of parameter space, a very non-trivial dependence on this result on the parameters you choose for the problem. Turns out we all chose those parameters in the beginning and it creates an expanding binary. But I would argue, and we have good evidence for, that when you change, for example, the thickness of the disk, the viscosity, the only few parameters we have in the problem that I set out for you, you change this result. And I'm not going to go into detail on these specific ones. I'm just giving you an idea what it depends on: the thermodynamics, the thickness, the viscosity, and the binary parameters, the mass ratio, and the eccentricity. So what I want to do is pick two of these, which will be eccentricity and disk thickness, and show you what we've learned from carrying out high-resolution simulations of this problem in that parameter space and where it's leading us. Okay, so orbits expand, but not always. Let's start by looking at disk, or binary, excuse me, binary eccentricity. All right. This movie on the left is the one we already saw for very low eccentricity near circular orbits. And what we've done is, of course, just do this for same calculation for different eccentricities. And the numerical experiment is to take that circular binary, run it to quasi-steady state, and then very slowly, in one long numerical calculation, increase the eccentricity of the binary on tens of thousands of orbits and measure the response. And that way you get a continuous response of the binary over time in some type of zero disk mass limit. And this is all for equal mass and the same aspect ratio that I showed you before. Okay, so what do we get? I'll go right to it and show you another plot with lots of colorful lines. This is the response of the binary. So there are two colored curves here to focus on. The most important one is the orange one. That is E dot, the time rate of change of the orbital eccentricity. The purple one is the same thing for the semi-major axis. But because E dot here for fixed mass ratio only depends on E, eccentricity, what this gives you is a phase portrait of the system, the behavior of the system. So let me show you what I mean. Let's look at the orange line. So when the orange line is below 0, the binary wants to become more circular. When it's above 0, it wants to pump eccentricity. If I pick an initial condition for my binary that's like 0.05 eccentricity, then it'll decay back to this point, which is the point we just looked at. So that's an attractor, circular binaries. Circular orbit binaries. And you look at the purple line, it's expanding. So those are circular out spirals we just looked at. Okay, but what if I pick initial condition here? Mid-eccentricities, or here? You can see that the binary just pumps eccentricity to this point. And if I were to start here, you'd see it goes to this point. That's obviously an attractor solution, another attractor solution. Okay, and I want to point out quickly these very sharp changes in the evolution here. Those, if you even simply just look at a movie, the movies we're looking at, you can see something very stark happens to the morphology of the disk here. The disk response goes from this eccentric cavity to a much more symmetric kind of m=2 symmetry, where the streams kind of stay equidistant to the binary. And then it pops out of it again as it goes to higher eccentricity at those two locations. Okay. The second location is quite important because that's the attractor. So let me just draw on here what happens in this phase portrait. The one I just showed you, you get circular out spirals. And here, it's a little confusing because those two lines cross. But what happens is that this binary, as it goes across this transition from a symmetric disk state to an asymmetric state, there's actually some lag time for that new state to pop in. And over that lag time, the binary is still kind of pumping eccentricity and decaying. And then it'll go back and it'll oscillate across that point. But because of the asymmetry of how quickly the binary is being pushed together versus pushed apart, it ends up, in the end, inspiraling around that eccentricity. So this is pretty fascinating, actually. You find, first of all, that circular out spirals and eccentric in spirals, these two attractors, are very different than the usual picture, and that they're caused by this very interesting disk state change in symmetry. And I wish I could tell you exactly right now what's causing that. And it's something that I've been working on for a little while now, from using tools with a combination of linear theory to more kind of pointed simulations. But if we can understand what is causing this state change, then the hope is that you can push this understanding to situations with more physics and different parameters. This is 0.1, I believe. Well, actually, this calculation was for a constant coefficient of kinematic viscosity. It was also done for an alpha, and the result is similar. All right, I want to say one more thing about orbital eccentricity, and this actually brings us into the realm of some observations for a moment. Okay, you can extend that. This calculation is extended for different mass ratios. Actually, Magda Sivek did this. And what you find is that equilibrium eccentricity survives. This is what we just looked at, equal mass ratios, equilibrium of 0.4. As you dial down the mass ratio, it survives. It just drops a little bit. Okay. So these arrows are showing you where a binary wants to evolve to in this space. That's the equilibrium eccentricity. And remember this picture from the beginning. This was one of the real ones, telescope real, from ALMA. This is in a circumbinary disk. And so there are a number of these observed systems that you can measure the orbital parameters of. And this is a plot from, so Paul Duffel and his student Alan Murray just put together these results for orbital evolution and then looked at what systems can we look at and plot on here. So there's a few. There are tidally circularized stellar binaries. Again, these are stellar binaries, not black holes. There are those in triples. But the most interesting one here are systems that are actually measured to be aligned with their circumbinary disk. And if you plot them on here, you can see that whether this is some conspiracy or not, they do fall along this line. So I think there's something to be learned here about, are we robustly hitting the features of what drives orbital evolution in stellar systems, or is this a coincidence? And I think it's pretty interesting, perhaps driving point here. Okay. So I know that we've looked at alpha and H over R, and I know that Alex Dittman, who's sitting over there, is finishing a long study of the dependence on H over R. So I'm very interested in seeing that, because H over R, I think, is one of the important parameters, because, you know, that's the next part of the talk, actually. Yeah. Okay. Let's keep going. That was story one on binary eccentricity, disk morphology, and possible matching of observations. I believe this is CO. Yeah. It's not. Well, what we should actually look at in this paper are which systems these are and exactly how that's measured to be more clear about each of them. Again, this is a paper by Paul Duffel and his student. So we did look at some other possibilities here with Kepler eclipsing binaries, but yeah, we could look into that some more. All right, next story, disk thickness, as Elliot brought up. Okay, everything so far has been for actually what are relatively warm disks, H.1, which is probably around what you might expect for stellar binaries. But for black hole binaries, we actually expect the disk usually to be a lot thinner, a lot colder than what we've been looking at so far. So we have isothermal gas so far. It means we can just change our H and look at the response. And that's what we're going to do. And a lot of this work I'm going to talk about in the next few slides is done by postdoc Chris Teedy at the NBI. And so he deserves most of the credit, all of the credit for the first part of this. And then at the end of what I'm going to tell you about here is some stuff we're currently working on together. All right, throughout you'll see this little h. It's the same as 1 over what is often called the Mach number, in case that is confusing. Okay, but what's the result? Thinner disks also tend to go away from these outspiraling solutions and drive in spiral, and sometimes very fast in spiral. And I want to explain why that is. So here's a nice series of plots from one of Chris's papers where they dissect the torques under the binary from different regions in the disk. So if you look at torques on the binary only from this inner region around the mini disks in red, you see this really positive torque trying to push the binary apart. If you look at the outer disk here in yellow, you find a slightly negative torque on the binary. And if you look at the region in the cavity where the streams are going in and out, that is actually the most strongly negative torque on the binary. Okay. So what you notice then is that as the thickness or the disk becomes thinner and thinner, so this is a thinner disk than that, you get this really high density pileup. That's what that's what white means here, very high density. So essentially, thinner disks get this higher density in the streams in the cavity region, which ends up causing a net negative torque. So, okay, that's an observation, but why is that happening? If you zoom in on how these streams, remember these accretion streams are mediating the steady state in the disk, how these deliver gas to the mini disks as you change the disk thickness from thick to thin, you see that they start to become very inefficient for thin disks. Essentially, the stream itself is much thinner, and when it comes in and shocks onto the mini disk, it can deliver less gas per orbit, per stream. All right, so the streams become less efficient. But what that means is that if you're going to go to steady state, which we're requiring here, then over time, you'll just build up and build up and build up the gas density at the edge of the cavity so that these streams, even though they have such a small funnel, will deliver enough mass to keep you in steady state. This results in those large densities and the large torques. That is set by a choice of the viscosity and the disk thickness. Yeah. So I think these simulations specifically have, yes, fixed. These may have fixed that outer boundary. Other simulations we have done have a log radial grid so that it just becomes, so that it can push out through there. But yeah. Okay. So yes, boundary conditions aside, which are important, we could discuss more. This picture, yeah, sorry. Yeah, so this picture is telling us that the thinner, cooler disks can't deliver streams, and you're causing this gas pileup, which creates this negative torque. So you can see that here, the top panel is just showing that you're in steady state. The accretion rates match. And on the bottom, you see for these thinner disks, the torque that you deliver per mass that you deliver becomes enormous. And that's because if you look at the density, the 1D azimuthally average density, just look at the solid lines, that density climbs orders of magnitude from where you started it in what you would have assumed for a single black hole. So it is true that once you're in steady state, you can get these enormous torques, but the question of how long does that take, right? So what you're finding here is a few things. One, that these disks can drive very fast in spiral, very fast, but that's in steady state that takes a very long time to reach. That can be longer than you expect the disk to last. And so these might be initial condition dependent, very thin disks, the solution for what is the orbitalization and the accretion, because during this early stage, before you reach steady state, the accretion onto the black holes is also choked. And I think importantly for understanding the physics, this identifies that process of stream generation as I think one of the more important ones in this problem. It also means that now we need more physics. That was isothermal. So we found from an isothermal simulation that you arbitrarily make the disk thinner, pressure less important, and this happens. But what should the disk thickness be? You might imagine that, okay, that H, that thickness we chose was for a single black hole knowledge. But when the binary is there, you know, kind of flinging these streams into the edge of your cavity, it could be heating it up, puffing it up, and making the disk thicker. So what you really need to do is self-consistently solve for the disk thickness, which is something that Chris Teedy and I are finishing work on right now, and I want to show you some preliminary results of this. This is the same type of movie I've been showing you, but now this is no longer a likely isothermal equation of state, but one with a black body cooling function. Still 2D. Okay? So we're essentially, if you put a single black hole there, we've just reproduced Shakura-Sinyaev solutions, but we put a binary in there. And we put a binary in for disks that are thin enough, and this is the numerically challenging part. These are very thin disks that the accretion rate you would expect now, because we've chosen a disk thickness, would be of order Eddington. Usually if you pick a very thick disk and do this, what you're finding is that, well, you're just imposing very super Eddington rates. But this is a more realistic in that sense. So this is a very thin disk with cooling. And what I want to show you is what do we get for the solution for the disk thickness. So now this is no longer density, surface density, but this is the actual derived disk thickness in this simulation. So dark is very thin, and this is puffed up. So what you see, actually maybe it's best to see from this 1D plot over here. So this is the Mach number, which means thick, very thin. If you go far away from the binary, you recover the Shakura-Sinyaev solution, as you should. And as you come in, this dip to very thick or thicker disks than expected is from all these streams over here impacting and heating up the gas disk, which is what I expected, except what happens is now as this material falls back to where the streams are actually generated, it gets even thinner than what we started. with. Oh, in this plot? So this here, actually think of this color, this yellowish color is this value, Mach of 40 or 1/40. And then it shoots up to even higher than 100 in black here. But as I showed you in the last couple of slides, the important thing here is the thickness of the disk at stream generation. So actually, we're finding it's even thinner. And so this problem I just discussed is probably even worse when you add cooling. And so that's just a preliminary result. But I can say that, yeah, the disk stays thin where stream generation happens, where it counts. And so I think this is something we'll have to continue looking at and adding more physics to. For example, the stream generation depends strongly on whether the fluid is turbulent or how strong radiation forces are. But this is a work that we'll put out shortly. One interesting point, even though you inhibit accretion onto the black holes here, the system can still be bright. And that's because, you usually think of you have this potential energy and accretion, it comes down and you harvest that from kinetic energy. And you would think if you're only coming down to the circumbinary cavity, you don't get all of your energy from accretion out. But actually these streams, they grab kinetic energy, get close to the binary, are flung back out, and you're just redistributing that energy to lower energy parts of the spectral energy distribution, which will also be in this paper when it's out. So this could make these systems look different than we thought as well. And got about 10 minutes left. I'm not going to talk about this, but as I transition to the next thing, I just want to point out that we've done all this for retrograde disks too, or in the process of doing it. And there's some also very beautiful dynamics in that problem as well that are being done by my student David O'Neill, who defends his thesis next week at the MBI. So happy to talk about that later as well. That's the retrograde system. You can get all kinds of interesting dynamics with that gas bridge between the two. Okay, but in the last 10 minutes, I did want to talk about some possible observational signatures. So that was these two stories of what I think we are learning, what I think we can do next with the dynamics and the problem as we build up to more accurate physics. But now I want to talk about this part. Back to this plot, which you must love, because I do. I'm going to put a whole bunch of stuff on here that it was not the point to explain, but I'm going to plug a review that I wrote recently with Maria Carisi on now fill this space not with where are gas disks important for dynamics, but what are the electromagnetic and gravitational wave observational signatures in this space, right? There are jets, there are PTAs and LISA, there's maybe the possibility of resolving these things directly with VLBI, and there are spectral shifts of broad lines. And what you'll see in all these dots here are a bunch of candidate systems found from what I'll call periodic light curves. So that's, you look at these quasars and look which quasars have some periodicity in their light curve, and maybe that has something to do with the gravitational two-body problem, creating some periodicity and accretion. All of these candidates here, I would say I'm not confident in any of them are a real subparsec supermassive black hole binary. We just don't, this is a difficult problem. AGN have a lot of intrinsic red noise, which we haven't characterized well on all time scales. And to pull a signal from the noise, you need to know what the signal looks like. And so that's why there's a QR code if you like. We've put together a database of all of these that hopefully will keep growing with some more confident ones soon. But despite this problem, and I want to show a few things about what we're doing to try and characterize this signal, I think there's two really interesting parts of this parameter space that I'm excited about right now, despite this difficulty in pulling out periodicity from red noise. The first is over here. Remember, all these plots are overlapping with binaries that are in the PTA band. So if at some point the pulsar timing arrays can find a continuous source, so one big binary sitting there, it'll sit there for 100,000 years. That gives us time to try and follow up. That's the first part, all right? And we've been doing some work recently in identifying which host galaxies these systems would be in. The second one is that if you can go to much deeper fields, wider fields, look at more systems and probe the smaller black holes, so deeper meaning you can approach lower luminosity, smaller black holes, then essentially for the same, the time that a system spends here will tell you how probable it is to find it. And the time it spends somewhere is proportional to the period to a high power, to the 8/3, right? So you drop the period, it gets much less probable. But it also depends on the mass. If you go to lower masses, then that probability gets higher. So essentially, we can go to the smaller masses with the deep field and go to the shorter periods of the same probability. Then you can get many cycles. So then we could approach systems with weeks, months, orbital periods, and with surveys like LSST or Rubin, then all of a sudden you're not trying to look for 4 cycles over 20 years, right? You can get tens and tens of cycles and at least be more confident of the periodic part. The supermassive black hole binary part is what I want to say some words on now, and also in relation to how we might prepare for these searches, which are coming on very soon. So let me just run by how does a accreting supermassive black hole binary become periodic? One, the accretion rate is periodic, right? So on the right, you're just seeing the accretion rate onto that binary measured over time in one of these simulations. I mentioned it can be match that onto a single black hole in some cases. But of course, getting the actual light curve out of this will depend on further modeling of radiation and cooling. So that's one way. The second way, which I'm very fond of, I'll show you this cartoon picture of, is that relativity happens. Whether or not there is any variability from accretion, as long as it's bright, say one of them, the small one is bright, and it's kind of inclined to the line of sight, then simply the orbital Doppler boost will give you some brightness variations over time. If that binary is even closer to the line of sight, within the Einstein radius of its companion, which actually doesn't really have to be that inclined depending on the systems, you'll get that on top of that Doppler modulation, right as this guy goes behind the big guy, you get a symmetric microlensing flare. All right, this has also been modeled with ray tracing of these circumbinary disk simulations. And what I like about these is that, again, they're just from relativity, and there are some interesting tests you can do here. So the Doppler boost depends on wavelength. You can predict the amplitude of your variability depending on the wavelength you're in. That's just because the slope of my spectra, if it's this, the redshift, blue shift is different than this, right? So it gives you some nice multi-wavelength tests. And of course, the lensing flare is in a unique phase of that light curve, and it's achromatic. So what I've been doing recently to prepare for these surveys is starting somewhere by saying, these are the main sources of accretion variability. Let me put them all together and make some mock light curves. To do that, I've taken our circumbinary disk simulation and say for now that it's 3 disks. Each of them has an accretion rate that I can measure from the simulations. And from that, I can assign a multi-component black body. So I have a 3-disk multi-component black body for each of those disks. I can put that together with the variability I see in the simulations for each disk. On top of that, I can add the special and general relativistic effects of Doppler and lensing. And you add that all together, you can pick your observing band and make some continuous light curves in time. Okay, so this is a code that is now on, you can pip install, called bin light, binary light, hopefully to be bin heavy at some point in the future. But for now, you can see, you can get really a zoo of different light curves, because you can do this for any different inclination angle, eccentricity, mass ratio, and we're adding to it over time. The point is that we're building this to improve upon. Okay, and we're also using it as a test case right now to make mock light curves for LSST. Because some of these light curves have very strange features that you might miss from just a normal periodogram. A Lamb's gargle trying to pick out sinusoids is going to miss some of these features. So we've put bin light together with different realizations of intrinsic AGN noise. And there's a graduate student working with Maria Carisi at WSU that is now putting together 1.2 million of these light curve simulations for various different parameters and noise realizations. And the idea is that we can use these as templates to see how well we can recover these types of light curves, and then to improve on the signatures over the time. Okay, I'm just about out of time, but I wanted to touch on one final thing related to this modeling of the electromagnetic signatures, which will also tie back into how we're modeling the dynamics. And this is something I've alluded to a few times about going beyond the thin disk model. Thin disk model saying here, if you have an accretion disk that's near Eddington, it gets heated up from viscosity, and it can efficiently radiate all of that through blackbody, hence the composite blackbody spectra I was just showing you. But if the accretion rate drops, and if you get closer down to the black holes, then it's been well known for a long time that you can get a few different states of accretion. The one I'm showing here is a hot accretion state, sometimes called advection-dominated accretion flow. And this has been successful in trying to describe observations of accretion onto X-ray binaries, black holes and X-ray binaries, and the different states they go through, but also for trying to describe the different AGN we see in the universe. For example, very high Eddington rates, you have your kind of standard high accretion, radiatively efficient quasar type thing. But as you lower the accretion rate, the inner parts of your flow can turn into this hotter, thick disk. And those are dominated not by black body cooling, but different optically thin types of cooling, like Bremsstrahlung, synchrotron, inverse Compton. So the point is, this will look different, and it should also happen for a binary. So here's the quick thing that we've done in a paper that is now accepted in AppJ. We can measure the accretion rate splitting in these systems. So there are actually 3 accretion rates in this system for which to compare to whether they're below this critical rate for radiatively inefficient accretion. And then you can map out, so what states are available to my binary? And this plot is essentially mapping out that there are 4 different states. And I'll just show you a graphic that gives you an idea of what the outcome of that is. So the y-axis is just total accretion rate onto the thing. At the top is Eddington, and as you go down, it's lower. And on the right is the mass ratio, which tells you how much is split between M1 and M2. And the one thing to keep in mind is the smaller one always takes more of the gas. But if you look at what these states look like, there are 4. Blue is this radiatively efficient state, and the red is the hot puffy state. So you find that you get a really interesting mix of multi-component accretion flows, which can change your spectra quite a bit, going from these kind of black body composites here, optical, UV, and infrared, to now, once you get these hot flows, extending down to radio submillimeter and up to X-ray and gamma ray emission. And just like you can do this for a single black hole, split it into these composite spectra, now we just have multiple different states available from binary accretion. And I'm just going to end with this plot. We applied actually this as a proof of principle to a candidate called PG1302, which is a candidate from this Doppler boost variability, which fits quite well this picture, because for this system, you find from the measured accretion rates that the circumbinary disk is thin, high Eddington, and the secondary is high Eddington, but the primary drops because it's starved and becomes a radiatively inefficient disk, which means that secondary can really give you this strong Doppler boost condition. And so I'm just putting this up here to show that we've modeled in the spectra from our disk models in red, and then knowing that the primary has a jet, adding a jet spectrum, and then a heated dust component. And so maybe no surprise, we can fit the measured spectrum pretty well. You can probably also do this. You can do this with a single black hole disk. But what I'm excited about with this kind of direction forward is that now you can start linking these different signatures of binary accretion to each other across the spectrum. The thermal will be the variable part, actually the thermal and the synchrotron, given cooling times in the system. Okay, but you also have to model this heated dust, which will look different in variability depending on whether you have a Doppler boost or an isotropic variation. There's data from WISE here in red and yellow. The jets can have wiggles due to the binary motion. And maybe most exciting, though futuristic of all, if this is bright in submillimeter, then an interesting number to keep in mind is that the angular size of the Milky Way on the sky is about the same as the separation of a 100th parsec binary at a gigaparsec. So the resolution is there, it's just what does it look like? So this is what I'm excited about going forward. I'll leave this summary, and thanks very much.
Thank you very much, Dan, for an expansive talk. We have 5 or so minutes available for questions. Roman.
A question about this plot is a pileup when you had a variation of the Mach number. So in this case, were these simulations with constant viscosity or constant alpha?
This is alpha, I believe.
So,
Yeah.
Okay, constant. So there's an added, kind of impediment to accretion because the cavity is likely to be larger at higher Mach numbers, right?
Yes, you're saying in radius, the viscosity is not constant because it's an alpha. Yeah, that's true. But if you
have similar calculations with constant nu? just to see the effect of
So that's something we can do. We have a suite of these ready to go. This is the first one at one set of parameters. So it'll be good to look at how the viscosity actually changes that.
What are your the main directions for exploring 3D effects?
Main directions? Well, I think what will be interesting here is that if we go to, I think we need to go to 3D here to try and understand how much confining to the plane is affecting how these shocks are driving the shape of the cavity and also this stream generation. So I think now that we've identified some interesting points in parameter space and some interesting mechanisms, it'll be good to start doing those in 3D. And there are 1 or 2 3D simulations for the circular orbit case that have taught us that a lot of things are the same, but slightly different torques. But yeah, I think maybe looking at the equilibrium eccentricity in 3D and with other physics. So.
So I see the streams, they are colliding each other. Are they shocks? Where does most energy dissipated in this?
Actually, I don't know where most of the energy is dissipated, because they're all catching up to each other right around here. Yeah, that is something I could ask, but I had imagined it was being dissipated here where it's being heated through shocks. So that's why it's getting puffed up, because the shock heating there.
Thanks for the talk. What happens if you start from an initially distorted disk, let's say initially eccentric or initially dwarf?
So initially distorted. So you do still grow this asymmetry, but one interesting thing is, okay, this can depend on if your disk is infinite or not. That eccentricity in your disk can grow to different sizes depending on what is outside of this disk. But usually I've started with just a flat thing. I've started with a cavity. I've started with a cavity with a little bit of asymmetry, and it usually goes to the same state unless you really, really change things.
Yeah, so it's possible I missed this, but I don't think I heard anything about spin in your simulations. Have you looked at how the black hole spin affects the orbital?
We looked at this in the post-processing state, meaning that these are point masses. And so we can ask, given what we've learned about the gas there, is it going to, using prescriptions for spin up or spin down, what would it do to the spins? But we haven't put in spinning black holes and asked how does that change the dynamics. And we also have put in pseudo potentials, which give you some idea, but that doesn't, yeah, we haven't really explored that in GR.
Hi, thanks for the great talk. So if you're computing torque on the body, it will probably have 2 contributions. The gravitational drag from the matter outside, and there's a momentum flux going into this sink region. What contribution is dominant usually?
The gravitational torque is usually dominant, but you have to add all of those up. That's right. There's an accretion of mass and accretion of momentum, but the gravitational torque is usually the strongest component that we find here. Correct me if I'm wrong, but that's what I remember from almost all of these simulations.
Is the strong dependence on H over R either understood or understandable?
I think it is.
Consequence of the Lindblad torque and how they depend on H over R?
Actually, I'm moving towards the picture that can we just model that ballistic stream? It's pulled off from the edge. And so if it's a much cooler stream that you're pulling, well, first you have to ask, is it a little bit closer or further? I think there's not a huge difference there, but can we just model that like a tidal disruption stream and ask, in the cooler case, is it just that it's collapsing down? But, well, Jeremy do you have a point on that, Jeremy?
What about this 5 years ago? It should be a solution for sufficiently thin disk. There's no accretion at all. And there's a balance between Lindblad torque, which Elliot has brought up, opiate resonance, and the viscous stuff's trying to spread inward, but it can't because of this torque. It's analogous to putting a planet in a gap in a full disk. You know, if the planet's massive enough compared to the thickness, it will open a cosmic gap.
Yeah,
And what happens then?
but there are stable orbits in that case called horseshoe orbits. Here there are not. So if the disk was far enough, okay. No,
Disk, as you say, there's a mass pileup. And there's a self-similar solution for this. It's long ago. There's an inner region close to the binary where you have zero mass flux and an outward angular momentum flux. And then a break somewhere out there beyond which you have an inner mass flux. And different slopes of the two. But this is why I asked you about constraining the boundary condition. If you force accretion at the outer boundary, you can never get this expanding. Well, I should talk to you more.
yeah, I mean, this has been done without the infinite disk with just a torus. It's the same result. But yeah, it'd be really interesting to talk about this. The steady state solution out here, I think the disk has to be far enough away that it's not being perturbed kind of catastrophically by the binary. Because in the gap case, you do these horseshoe orbits and gas can come in and stably go from inner to outer. And so you get this steady state. But okay, yeah.
Excellent. So with that, let's proceed to the call lunch and thank Dan once again.